Here we are. We're live.
I think we went live. Or are we now live and we weren't live before? I felt alive.
Now I really feel alive.
Hey, have you seen? Hello, everybody. By the way, welcome to Coriolis. Ben Jordan, Bill Hurd coming at you, just chatting away.
Yeah.
Hey, have you seen that somebody said that the AI at Google is sentient? And they showed the responses and they'd be perfectly programmed responses for an AI, but he's saying, no, it's alive. Did you see any of that?
No, I didn't. What is the true test for sentience?
Right. It answers the questions like I would. Well, you can teach that. So what is
the database can do that with a good search.
Yes.
Which is what Google is. But I mean, yeah, I don't think that's it. I don't think that's the test.
Right. So, well, I got a couple new toys I want to show this week, but I learned something about a component this week. My friend Hedley Davis of old Commodore and Xbox and 3DO fame was here, and he told me about this part right here. And I had to re-Google for it and whatnot, but as you know, ceramic caps came on the scene and they were wonderful, right? Yeah. I had used tantalums. I had used polymers and stuff. And then ceramic came out and it was like, you mean I can do that and not be polarity sensitive? So it was just wonderful, except for size. Right?
Okay.
So one of the problems with size is it gets a moment of inertia or a vibration, or there's real names for it. I'm making these names up. But with vibration, it's brittle, right? It's ceramics. So what they've done is they've got a soft termination feature, which is supposed to absorb vibration.
So they've
not supposed to, it does.
So these are MLCCs, but they're somewhat more flexible.
Yes, that's my understanding.
To resist shock and vibe and be for harsh environments. So you mentioned automotive, which is, we're taught in IPC training, it's probably still the truth. The engine bay of a motor vehicle is the harshest environment.
Yes, hell on earth.
It has the most extreme of temperatures, and it has all the vibration, and it has all the worst chemicals you can imagine. It's all there in one place.
Right. You know, I was an EMT when airbags first came out.
Oh, did you see airbag injuries?
I've seen injuries that would have been a lot worse without airbags. That's what I've seen. And I've seen the imprint on the airbag where the lipstick and stuff, we call it the face of life. It's where the makeup transfers to the airbag, though I would hate to be the person that had been wearing the makeup.
Yeah.
But
I've heard like airbags can be dangerous because to get them to inflate fast enough, they have to use an explosive.
Yes. The explosive, there's sodium hydroxide in there, and people thought that the powder coming out was sodium hydroxide. But it isn't. That's just talc to lubricate the bag as it comes out.
Talc's generally benign, although it was banned as baby powder because adults were using it for private parts lubrication, to avoid itching and sweat during the day. And it was leading to cervical cancers. It was linked to cervical cancer. So talc is one of the best dry lubricants for your fingers as a guitar player, but it's hard to get now because of that. They replaced it with corn husk in baby powder, and corn husk just doesn't cut it for a dry finger lubricant for a guitarist. But anyway.
Okay. So what I remember though about when the airbag first came out is the car companies did meet with fire departments and stuff. And a guy that went to GM's demonstration, they said, oh, of course the airbags are safe. We would never put something dangerous in a car. And the guy's like, excuse me, you're putting sulfuric acid in batteries. You're putting gasoline. What do you mean you're not putting dangerous stuff on cars?
Yeah,
we put these fires out all the time.
That's outrageous.
Yeah. But I've never done, I stopped being an EMT long before the electric vehicle revolution. So I have not yet tried to put out a fire, a battery fire. So
that could be a lot more difficult.
Yeah.
I think that's still a big question mark for all of us. But I think given all the other technology that comes with electrification of vehicles, so self-driving modes, all the sensor technology, I think ultimately it's all going to get way safer. We're heading for, I don't know if you've seen the movie with Tom Cruise, The Minority Report.
Yes.
It's a great movie. But in that, they have these cars and they're all electric self-driving vehicles. So you can just sit in the car and lounge while you're going somewhere. And they all go together on these freeways and they're locked in like in a pocket. And
right.
It's actually because they all travel at identically the same speed and perfect distance from each other. Everyone has a predictable commute and like it's kind of boring. It's too perfect in a way.
It's like TCP packets.
These movies explore the concept of with freedom comes danger. And I was actually telling my daughter this morning because she had her first real fender bender yesterday, unfortunately, and she was crying. And I was just trying to encourage her like this. Look, it's not a bad one. We got to get this out of the way, learn from it, and become a better driver. It's just part of life, really. Almost everyone has at least a small accident in their life. And I've had far worse ones. But I'm saying it's also, she said at one point in the conversation, she said, why does it have to be so dangerous driving? And why is it so risky? I'm like, that's the price of freedom. You can take away all risk and then you end up with a society where no one gets to do anything interesting.
And picture the 60s.
You pick one or the other. You choose freedom or you choose restriction and safety. And you can just live a life in the matrix and arrive safely at death, having done nothing remarkable. That's how it goes. That's life.
Yeah. So picture the 60s, though, where, I mean, I grew up where seatbelts were an optional add-on, right?
Oh, my gosh, that would have been so bad.
Yeah. Yeah. And we rollovers, all those things. So
I think we can all agree there are certain restrictions we bring in that we really should have.
Right.
Yeah.
So I've got a piece of equipment. Now, I talked about it one day when you weren't on that day, but it's called the Joulescope. And Matt Liberty had sent this to me after Mike Vikes hooked us up. He loaned it to me, and it's an interesting piece of equipment. I used it to analyze the initial power draw of a switcher supply when you first give it power. And the problem is it's a once and done event, right? How do you capture that? How do you capture seconds worth so you can win it? You
wanted to capture the inrush current, basically.
Right. So I've got this thing called, and it's on my, you know what? I can try and show, but let me show you the screen of it first before I show a picture of my bench. I don't know if you can see my bench behind me. It's a mess today, which is good. It means I'm playing with lots of things.
That is good.
I'm actually running a Bode plot through a switcher to try and analyze its feedback loop, its phase margin and noise and stuff.
Oh, very cool.
Yeah. So that's my other piece of equipment I'm playing with. But here's what I got when I turned on the switcher. And that doesn't look like much, but what I can do in theory is I can keep expanding in.
Oh, look at that.
And I can see the moment it turned on, and look what happened. It starts at 0 volt, it's 0 current, and jumps up for a cycle during the turn on, and then drops to its the value that it'll coast at. Here, I'm going to put a load on it. And
I like that. And we're also seeing, if we look at the voltage waveform, we're seeing that, I'm guessing that's at the input.
This is at the input. That's right.
So that's very
it actually reads out in watts too.
So it looks like we're looking at the switching. I'm seeing the switching waveform superimposed on the input
right
voltage there.
You were. So I realize that's a bunch of garbage. Let me try and get a new capture going here. So I have to do this remotely, unfortunately. So there it goes. Now let me stop, zoom out, and zoom back in. And here is the event that I just created.
Well, that thing seems to have quite a deep memory, which is nice.
It's got a real deep memory, and he does some math for you. That's the really cool part here. And there's our waveform again. And you can I'd have to look at this frequency to see if that's the switcher frequency or an oscillation going on.
Yeah, it looks like the switcher frequency to me.
Right, right. But it reads out, like I said, in watts, which is watts is an easy formula, but sometimes it can really, you're trying to get the dynamic wattage. I can zoom in on any part of this and get the wattage right under the cursor.
Yeah.
Yeah. So this is the joule scope. If anybody's interested in one of these, reach out to me on our Discord channel. Ben, what's our Discord channel?
Coriolis-effect.com. There's a link at the top of the page. Let me throw the banner up again. Let me throw the banner. There it is.
Ah.
Go there. There's a Discord link at the top of the page. So the joule scope, we're looking at a screen there, but that's that little metal box on your bench. Go back to your camera view.
Here's the bench.
So it's that little metal box, right?
Right here. Yes.
And so all the rest of that's done in the software. So basically, I'm guessing it is a USB instrument.
It's a USB instrument, and what it's known for is scaling. So it's got integral resistors, and he will scale for you. He switches in and out the resistors to get that current measurement. As you know, you're trying to get a current measurement without messing up the circuit that you're measuring can be tough. And he auto scales the resistors to not only keep your circuit working, but to make the readings valid.
So question, what kind of bandwidth does this thing have? Because it's got a switched output that provides power to the device under test, right?
Right.
And you provide power to it. That's what I'm seeing through the two banana leads leading up to your higher shelf.
Right, right.
So your power comes from a bench power supply. It goes through this thing, and it switches the power on with its internal, maybe it's got some solid state relays or something.
Yes, yeah, it's got something going.
But then it's also through that connection also measuring the current. Is that correct?
Right. Now,
so the only other connection to that metal box is the USB to the host software.
That's right. So power in, right here.
Yep.
Power out, and the USB in the back.
Okay. And so that's going to be somewhat bandwidth limited based on the types of connectors being used.
Right.
But then again, that's all. If you're testing a power supply and looking at inrush current and things like that, you don't need a massive bandwidth.
No, you don't. No. So that's what I've been playing with. Again, thank you, Matthew, for loaning that to me. Whoops, let me get you back in here. Boink, there we are. Here, let's do this one. I like that one. But it was very, very useful because I was digging down so low in batteries. I was working on LiPo batteries, which are like 3.9 volts type area. Yep. There's not a lot of room to play in. And here was how you previously do it. Is you need one of these. This is a 0.05 ohm resistor. And I would, this is a 0.01.
Yep. And that's can be tricky to measure the voltage drop across.
Right.
Those.
You need an isolated probe, which my Keithley 5.5 digit does. So basically, you put your probe on here and run E equals IR across it to figure out what your current. But that gives you a readout. It doesn't give you, here's what it did during the turn on, which is the joule scope is so cool.
It's much nicer if you have an oscilloscope view. So I've recently made similar measurements on another circuit I was working on using scope probes.
Right.
And the board itself had a current sense resistor built onto it. It was just a 0.1 ohm resistor.
Right. Okay, so I have a topic for you, and then that leads into my next product that I actually purchased. But what's on a typical oscilloscope, like I've got a 5 gigasample per second, 1 gigahertz bandwidth, MDO 3104. What do you think the input resolution is on that in bits?
I was just using one. I borrowed the exact same scope from Mark Hughes for a couple of weeks, but I didn't look that up. I would say 12 bits.
It's 8 bits. Almost all scopes are 8 bits. And I heard Eric Bogatin talk about that at the Altium Live event a couple of years ago.
I should have heard that then, because I probably was there.
And what he did was he said, well, you got 10 grids, right, on the scope. You go, okay, 10 grids. He says, and there's little hash marks in there, like 4 of them. So let's say there's 10 readouts in there, right? And you go, well, that's 10 times 10. That's only 100 levels that the human eye can see on the scope. So double that.
Screen,
and, the eyes don't need much resolution because we're just looking at a display. But when I try to use my scope for a data acquisition system, the math was like, 8-bit clunky,
Yeah.
So now, did you play with the offset in your scope? That's the one thing digital scopes not the one thing, but a thing a digital scope can do that's really cool is if I want to look at a 5-volt signal, but I want it amplified, I can give it a 4-volt offset and bring it back down into the display.
Well, we learned to do that back in college in the 90s. My lab practice instructor, he was brutal. He was super strict. He'd examine us on our scope practice. We had a class called a lab and oscilloscope practice. And it was actually difficult to pass because we had to learn all those tricks. And even back then in 1993, that class was, we had old 20 megahertz bandwidth tech scopes in the room. But we were doing that. We were actually, to get the most accurate measurement, we would DC couple a waveform, set the ground point, and we'd go to the bottom of the graticule and go to the maximum peak of the waveform that fits on the screen.
Right.
And then, so we were using offsets even back then with analog scopes, but we didn't do anything like you'd want to do now with a digital scope with a power supply. But yes, you can say, well, I want to look at the DC mean of my output, and that might be 12 volts, say. But you also want to look at the ripple on that, which is a little superimposed AC over the top of it. So the way I would normally do that is the way we did back in the day with the analog scopes as well. I'd do the measurement using the DC, and then I'd flick the channel to AC coupled,
right,
and maximize the waveform and measure the ripple that way, and say, well, that's the peak-to-peak ripple superimposed over the DC output of the
okay supply. Got it.
So
yep. So I wanted a digital or an analog acquisition system. I wanted that 12 or 14 bits that you just mentioned that you think would be handy to have, right? For to do post match.
Well, that's it. If you want to do data acquisition, you really need 12 bits at least. If you want to do audio, you need 16. Unless you want to do early 80s lo-fi audio, you can get away with 12 bits. But if you go as low as 8, like we did audio samples using Commodore Amigas,
right.
But the little sampling board we made was a homemade kit design using ADC 0804 chip. And the ADC 0804 was an 8-bit. I think the maximum sample rate you could really push it to was about 20 kilohertz. So you had to bandwidth limit your input. It was really only good for phone quality voice. and not much else. That's about as good as you could do with 8 bits. But if you want good quality audio, you really need to go at least Redbook, 16 bits, 44K.
Right. I remember when CD players came out, right? My first CD player was $500, and you couldn't.
Expensive.
Yeah, and you couldn't like bump them. They had no buffering. Putting them in cars was problematic. We went to a CES show in the 80s where they showed this thing vibrating a CD player, and it's still playing at the CES show. So that was big enough they put it in their booth, the vibrate.
So that would have been a big deal. Yeah. My family, we didn't start CD. Sony released the CD at first. I think they were the first to launch a CD player and actually start releasing CD.
That's my memory as well. Yeah.
And it was 1983.
Yes.
A long time ago.
Yes.
My brothers and I did not start purchasing CDs. My parents didn't even buy a CD player until about 1991. That's how late to the game we were, because at first, they were super expensive, and
there wasn't a lot. Yeah.
So, and then once we had one, I'm like, oh, there's no going back. This sounds so much better than records, and no skipping, no fear of damage, no static, no dust.
Right. So the hardest thing was getting music on it originally, and it's like me and my friends, it's like of the dozen CDs I had, they had 8 of them too, because like an early one was Stevie Nicks, but you couldn't get Fleetwood Mac, but you could get Stevie Nicks.
Yeah, very few. Yeah, that's right.
So I wanted to invest in an acquisition system. I was talking with Mike Fikes on our Discord, and he mentioned the Analog Discovery 2 from Digilant. Now, as y'all may remember, I have the digital Discovery. So I use this as it may look like a digital logic analyzer.
Yeah.
And look at all the wires I have. Very cool. But I wanted an analog acquisition system. Let's see if I can share this screen and not look silly in the process. Share screen, window, boink, share. And so I invested in one of these. It's $399, and I got some options for it. But this is the Analog Discovery 2.
14-bit at 100 megasamples a second is actually pretty darn impressive.
I love it. Yeah.
That's very impressive.
And it's got 16K buffer, which is cool. It sounds like not the biggest, but it sounds fast and big to me. It also doubles as a power supply. Oh, so if you look here, you can use it as an oscilloscope. You can use it as an arbitrary waveform generator. There's 2 of them built in. And guess what my arbitrary waveform generator on my Tektronix won't do? It won't do a swept frequency. I have to use my old HP to do that.
Oh, really? You can't do a chip?
Can't do a sweep that I can tell. I should ask Alan to make sure, Alan Wolke, but I could not get it to sweep. But so that was another reason I wanted a modern swept arbitrary waveform generator. So you have that capability.
Look at this protocol analyzer.
Yeah.
Tracer, impedance analyzer, spectrum
impedance analyzer. It has a small module to measure impedance, but it's also a network analyzer too, which is very related. Let's see if
that's amazing.
I want to see if they showed the little add-on.
Of course, the bandwidth is limited to 10 megahertz, so
right. But see, that was my problem. Is all my stuff is high speed. I didn't have anything low speed, relatively low speed.
Mm-hmm.
So here they show you how to like measure the impedance, complex impedance of something, and they have a small module to assist in doing that. I'm going real fast because I want to see if they showed the module. No, I'd have to find it. So it's an impedance analyzer. So there's a piece of equipment. Oh. How about this? It's a curve tracer.
Yeah, that's a good one. I'd like to actually use that because I have some old JFETs from old audio gear and some old germanium transistors that I kind of inherited from my brother when he died, but he had collected a few obscure, hard to get parts that are sought after for boutique overdrives and things like that.
Right. Are they like the big old TO3 cases?
No, some of them are little metal cans that are this long, like half an inch long.
Right.
Yeah, they're all small signal parts, but I could really use a curve tracer to actually analyze them so I can deploy them in something, you know.
Right. Match them up to each other and whatnot.
So do you have this set up on your bench behind you?
I do. Let me show a couple more things it does, because once I show the bench, it's going to be boring because it's set up to do so. It's also a spectrum analyzer. For y'all that don't have a spectrum analyzer, I guess it goes probably up to 10 meg.
Looks like it.
So what you're hearing is all the justification I used for buying this. You can do static I/O. I needed to do this for a Hackaday video one time, and I actually made a PGA act like just static I/O lines, just because I didn't have a way to turn on and off I/O lines, so it can be a easy to use GPIO source. If it sounds like I'm plugging these people, I love my new toy, so I'm plugging them. It's a pattern generator. So that my digital does that as well. And data logger and voltmeter and an oscilloscope. So it's all of those instruments in one. But the main thing I like about the oscilloscope is it's got true differential inputs. So they can float up to 50 volts is my memory, you know, before the common mode becomes a problem. So that means I can put an oscilloscope probe across the input resistor.
That's really useful. The one thing you have to bear in mind with differential probing and the common mode range, they may say you can go up to 50 volts, but that means if you have a 50 volt, your signal on any one of the lines can't go up another 50 because that would push it to 100. So it is gonna clamp the signals at 50 volts if it's got the protection for that in it.
And it says all over it, please ground it anyways, or you may get noise and stuff.
So what it really means is
the ground lead, not the differential leads.
Yeah. What you really need to do is in your mind say, well, that means I can allow my common mode up to plus and minus 25. So, and if my main signal is only a 3.3 volt signal, then the maximum common mode I can allow is really 50 minus 3.3, you know, so 42.7.
Yeah, let's see if I can. I'm looking to see if I have a picture of the front end of this thing where you can see the differentialness. But so I do have it on the bench, and one of the things I am doing, as I already mentioned, is I'm injecting a signal into. Let me see if I can find a picture. I'm actually going to go to our Discord and pull out something that I had sent them.
The Swiss Army knife of test gear. It sure looks like it.
Yeah.
Now I'm looking forward to the future where they have one of these and it has 100 or even a gig bandwidth. Imagine doing all that stuff with a gigahertz bandwidth.
Wow. Yeah.
Then you have a really amazing tool that you can do anything with. Yeah.
So one of the things I was curious about was when you do switching power supply design, you can use the tool. And, you know, the tool from TI, it's WebBench. From Analog Devices, it's LT PowerCAD. And it'll tell you and predict the phase margin, the gain, and all these are words for stability. Well, what they don't really do is talk about the influence of the PC board, though you could simulate it with that if you're smarter than me.
Well, that's where the expensive simulation tools that that do extraction come in. So that's what Agilent ADS, or they call it Pathwave now, answers. Some of those things, they actually import your board design and they use finite element analysis to do the extraction of the actual layer stack and all your traces and everything.
Right.
And then that can be used to generate either S parameter models or impulse responses that can be fed back into the rest of the circuit simulation. But that's what signal integrity analysis tools do, and those can correlate also with the instruments. So you can simulate it, and then you can build your prototype and measure it in a TDR or oscilloscope, and you can say, well, these waveforms are basically identical, so we designed it right.
How at a big company, I got the impression, this was new to me, and I learned this from the Altium Live event, from meeting all the people that were there, and I realized that in big companies, you'll have a design core, but then there's a signal integrity group that layers on top of that. Is that how that's done? You have specialists, big enough company like Cisco or something like that.
Usually up to now, that's how it is, because those people have gone out of their way to learn. Because here's the thing. Anyone who studies electrical engineering will learn about electromagnetics at that fundamental level and can understand this stuff. But then when it comes to printed circuit boards, most of the learning happens after school, when you're learning to drive test instruments and simulation software, both of which are very complex and can take years. Like you'd say, even learning CAD takes years to become a master. So if I want to be a really efficient designer using Altium, it took me 4 years working at Altium and using the tool and learning how it works, so to promote it, make videos, support customers. I did a lot of customer support. Right. And after 4 years, I confidently said, yeah, I'm an expert in this tool. And I would say KiCad would take probably a solid year at least. It's a simpler tool. It has less features, so it would take less time. But it would still take, I'd say, about a year of consistent working with it to become really expert at it.
Right.
And simulators are another order of magnitude more complicated, again, with all the options and knowing what all the options mean. You have to learn things like, well, so if I'm learning signal integrity, I need to know, what do we want to do with this? We want to know that this trace on this circuit board is going to carry a signal from here to here, and the receiver is not going to get distortion or misinterpret that signal. Right. And that signal is a series of bits, and those bits could be random. And actually, the number of ones in a row and the number of zeros in a row at those high speeds starts to put a DC bias on the transmission line. And so we start to run into problems. So what you realize is you can't just use a square wave. You can't put a clock signal down a line in a simulator and see that there's a little bit of ringing, but it still looks pretty good. It's like, that's the simplest SI you can do.
Right.
What you really need to do is put a very long pseudo-random bit sequence. So now you start learning, well, what are they? What are the standards in the industry that we go by? We do a PRBS, pseudo-random bit sequence.
Right.
And how long do you make it? Well, I think I'm going off the top of my head here, but I think an 18-bit PRBS is or PRBS 18 means maybe it's generated with an 18-bit long, it's pseudo-random bit sequences are generated with a circuit that has XOR gates in it and some different feedback loops, right?
Right.
And you can make those longer to make the randomness go for longer before it starts repeating the same pattern again.
Right.
And the longer it is, the more quote unquote random it is. It's of course not random. That's why we call it pseudo-random. But anyway.
How good are those?
You have to generate that in software and then simulate that going through your transmission line. And then, so there's all these things you have to learn, and it just takes time, right? There's a lot to it. So, and the best tools, I think, for that, which happen to be really expensive, because the truth is, to build simulation tools that give you a very clear and very close to reality, because it's very easy to simulate something, but the simulation is ideal and totally nothing like what you experience when you build the thing, right? We've all done that. We've all created a circuit and simulated in Spice, and then we build it on a breadboard and it doesn't work. Like, you go into Spice, you design an oscillator, you put it on a breadboard, it won't start ringing.
Right.
You got to get it to start somehow.
Right. So startup state's a big thing. Yeah.
Very big difference between a simulator and the real world. And the reason some of those SI tools are so expensive is because they've fixed all those problems in the software to make it as close to the real world as possible. And then on top of that, they have to figure out ways of making it out of the box most like the real world to start with, so you don't have as much setup work that you have to do to get it going. And there's that, and there's expertise and secrets in all the algorithms for Bode parameter extraction, finite element analysis, and optimizing those algorithms so that they run fast, because there's open source tools like Cook Studio or OpenEMS, which are really good, and they do finite difference time domain. They use the classic E algorithm, and they work great, but they take a long time to simulate something because they're just using the open source knowledge of the algorithm, whereas some of these commercial companies like Keysight or what's the other one, Ansys, SideSoft, and others, they have very clever software developers who've looked at those and found other ways to optimize them and get them to run really fast. So that's kind of what you're paying for. But
so when you're done with an analysis like that, how confident would you be to say, yes, the circuit and the layout and the cabling and the interconnects all can do 56 gigabit per second and have a bit error rate of X, right? Because don't we always, we give a speed, but then we need to give an error rate that goes with that as far as our expectations.
My confidence in that, from a simulation point of view, because I've never done a lot of it, is lower than someone who does it all the time. And this comes back to your original statement and question, is why do bigger companies wind up having dedicated SI employees,
right?
Signal integrity engineers. And this is why. It takes time, and it takes a few design cycles where you've been through it, where you've actually done the simulation, that's guided design, you've re-simulated, and then
you've built
it, and then you've measured what you built,
right?
And maybe it was different, so your confidence is low that you set up the simulation correctly. So you learn from that, and then you go back and re-simulate with some differences and different settings, and then you realize, oh, well, now that matches what we measured. Or perhaps what we're measuring, we're not measuring it correctly.
Right.
We've got our instruments set up wrong, which happens a lot.
Right.
So once those things are all ironed out, those people develop a skill set where they know, like, this is the checklist I go through every time, and for this kind of scenario, this is what would be needed, and they can apply that over and over again. So they become experts, and sometimes the use of the software, the use of the test instruments is so expensive. The kind of person you want in that role, because you're already paying a lot for simulation and you're paying a lot for test, you want someone who can shorten that,
right,
the amount of time as much as possible. The tools allow them to shorten it if they're experts in driving those tools. And
right.
Back to what I said before, it can take years to become an expert in a particular tool. And frankly, EDA software companies, the reason the prices of commercial EDA software are so much higher than other regular software, there's two reasons. One is the total addressable market is very small compared to regular software. So to get the ROI, to pay for the engineering of the software, it requires more money. And there's fewer people to pay that money, so the license costs are going to be higher. It's unavoidable. But the other reason is the other reason is that there is some gouging going on, especially with the high-end tools, the quote-unquote high-end tools. There is some gouging going on because they know, like, if you're an expert in our tool, you're not going to switch to another tool.
Right.
Your whole career is built around this tool. And if you want to go do something else, you'll be starting again at the bottom.
Right.
So, like, it's very hard for me. I could easily get a job as a full-time hardware engineer at pretty much any company that uses Altium, because I'm an Altium expert.
Right.
But if they're a Mentor Expedition house or a Cadence Allegro house, I'd have to fight for the job, and then I'd have to spend a year just learning the tool.
Right.
And then another 3 years after that being uncomfortable with it until I'm an expert.
Yeah.
And it's like that. These EDA companies, they know this, right? We all know it. And even people who use KiCad because you just do a few boards a year and you're not employed to do board design, so you don't have a commercial tool budget. Once you've gone through the pain of learning that thing, you're kind of loath to change it. Let's be honest. Anyway, I'm on a rant now.
No, that's all really useful. I had an Altium issue this week where I went to 3D view and the whole thing's just blown up, right? There's this big yellow box right where my circuit should be. And I ran a bend simulator and the bend simulator said it's not a bug. So I said, okay, I'm operating it wrong.
You have a bend simulator?
Yes. Instead of bothering you with, but in real life, when you work at a company in a CAD department, you're working, or not a CAD department, but around CAD terminals, you can turn to somebody and say, what's this doing? And if they know, they'll chime in, right? So a group of people in a room is smarter than, a bunch of people on Zoom, right?
Oh, yeah.
So I ran the bend emulator and I reached down and I hit Shift C, which I had never done in 3D mode. And suddenly I could see my image again. The week before, all my 3D bodies had disappeared. I Googled for it. Honestly, I'd rather read a manual than Google for it, but I Googled for it and I reached down, I hit Shift Z, which turns your 3D bodies back on. I'm like, okay, Google, you just acted like that other engineer in the room for me.
Yeah.
So, yeah. Let's see. I have something to show. My screen's been blocked, so I don't know if you've been able to see me all this time, but let me share this. So
I can see that.
Yeah. So
you got Mike's on Discord in the background. Hi, Mike.
Yeah. Hopefully this is sterile.
We just see the list of people. It's all good.
Yeah.
Okay. So Bode plot measurement setup with a Rode and Schwartz.
Right. I just happened to Google that.
To say that. Is it Rode and Schwartz or Rode and Schwartz?
Well, is it Bode or Bode?
I'm hearing it both ways. I don't know.
Yeah, and Mike corrected me on my pronunciation of Bode earlier. I was calling it Bode, which I
always called it
the 70s. Yeah.
Bode sounds too much like B-Day to me. I'm sorry. I'm going to
stick it sounds like hoity-toity. Yeah, right. But what
Bode. Yeah, it's actually, that's like Bordeaux. It's like some kind of wine.
So
give me a Bordeaux plot. It's 5 p.m. somewhere. Anyway.
So my question started as, how do you run a Bode plot? Okay, let me back up. A Bode plot is useful for telling you the frequency response of a circuit.
And the phase.
Including the phase and amplitude information.
Right, because you
Which
want
basically is your real and imaginary parts, right? That's
yes.
what we're saying.
And why do we want that? We want to know, is our circuit stable?
Stable, right.
And stability is the hardest thing. Like, people design just a point on that. The reason you do this on a power supply design is for stability. You want to make sure it keeps regulating no matter what. Unless you go way outside the bounds of the limits you've set, it's got to keep regulating.
And not oscillate.
And keep the voltage.
And not burn up in the process.
Yeah. But you could have a pulsing load. Let's say you had a load that had a particular clock and it was delivering heavy current. So let's say it was another PWM like a Class D audio amplifier.
Right.
And it's delivering a heavy current that's switched with a PWM at a fixed frequency. That frequency could interfere with your frequency and the frequency response of the power supply regulator circuit, right?
Right. You can step on each other.
The whole thing out of regulation, and you could have things blowing up.
Right.
So this is why we do Bode plots on power supplies and other things.
So correct me if I'm wrong, but if we look at amplitude and phase shift through a circuit, knowing there's feedback, when I get to 180 degrees of phase shift, if there's gain, I'm oscillating. Is that a good summary?
Yeah.
180 degrees phase shift total plus gain is round and round you go.
Yep.
So that's the other thing you look for in the response of the switch power, is to make sure it doesn't become a self oscillator, independent of what the voltage and the current's trying to tell it to do. So
I have to. My mic batteries are about to die. Keep going.
Okay. So I'll keep talking. So what I did was I wondered, how do you do this on a live circuit? If the circuit is not powered up, I can inject a signal and then see what that looks like on my scope, or in my case now, my new acquisition system. But how do you do it on a powered up unit? And so I Googled around, asked some people. Mike Fikes and I have been talking all week, and we came up with this example where we end up with a resistor for the as a rejection point, and they call it reverse impedance. That impedance that we're putting the signal in is so small compared to the impedance of the rest of the circuit that between that and the signal strength, what you're doing is small signal analysis on a large signal system. So you may be generating 12 volts, but you might be injecting 0.2 volts into that to see how it operates. And that's where this diagram comes from. We use an injection transformer to isolate the generator, the waveform generator. And I used a Coilcraft. I went through their catalog, found one I liked, injected it. And then you need these differential inputs to measure across that to see your response. So again, I'm using my Analog Discovery 2. I just hooked it up this morning. So I'm getting results that I can't yet explain, other than my transformer has a bad low end on it. Hang on a second. So, and let me show you my Bode plot.
So what it amounts to, though, is you're measuring the voltage and the current through a resistive load to see the phase relationship between the voltage and the current.
Right. Yeah, people want to know where I can get a Bend simulator, by the way.
I guess I'll have to make one.
Discord. Yeah, or drop by our Discord channel.
I'll have to put my brain into some AI and make a plugin for Altium that when you're running into trouble with Altium and you want to know what to do next, I'll just suddenly appear like Clippy and say, hey, I think what you're trying to do is go to the project menu, drop down. Okay, go to variants. Okay, now this is where you add a variant. Click add variant. Okay, now click OK. Go back to the project panel. You can see the variant there. Select it. Now go to the second tab on your schematic. Now you're looking at that variant. Click the little red X on the active bar, and you can click over any component you want to be not fitted for that variant. Bam. That was a YouTube short, people. I'm going to do that.
I didn't know how to do variants. I'm going to have to load my Bend simulator with your answer, you know. So, Yeah, variance. And, you know, next week, maybe we can talk about variance in Altium and maybe panelization rules.
Actually,
and stuff.
Everyone needs variance more than ever. I'll tell you why. Supply chain. Hello.
Right.
I actually had to use it for a design job. I just finished with someone that they'd originally spec'd a linear regulator on the circuit that,
like an LM1117 by any chance?
No, it was an even smaller one by Taiwan Semiconductor, just an obscure 5-volt regulator, tiny little package.
Right.
They were available in Taiwan for like, they were gouging. They were totally gouging. Their parts were available, but they wanted $5 each for them. It like totally mind-blowing, outrageous price. So I'm like, I went and found 2 alternative microchip parts that had the same pinout and were basically drop-in replacements that were less than $1 each.
Now, did you use Altium to find that alternative, or DigiKey, or how'd you do that?
In that instance, I was using. No, I ended up Googling it. I started out using the Active Bomb tool. And I used that to close the loop, to put the links to the parts in the schematic. But in my research, just to be really thorough, I Googled everything. I just searched for 5-volt linear regulators in this particular package and found a bunch, and they all kind of were equivalents by different manufacturers. So there were a lot of options. Some of them were overpriced and some weren't available. And so I made 2 other variants of the board.
Okay.
To fit different parts in that position. So yeah.
Totally I need to learn to do that. Yeah, and a lot of people are scrambling to redesign stuff just because of the packaging of the chips that are available. Is what I've gathered.
Yes, you can't get an Atmel, SAM D21 for love or money right now, but you might get something. You might get it in a chip scale package, perhaps, but then you're going to be designing a much more expensive board, right? It's going to be micro vias and
right.
All that sort of
I just got an order of CP2102s in, and I had to use a QFN 28. So
I even had trouble. I even recently bought, just off AliExpress, a little 10-pack of the CH341Gs, which is the Chinese version of those, USB to serial devices. Even those are really hard to get right now.
Yeah. So we're almost done here for today, but I did want to show this. Let's see if it shares. So this is my Analog Discovery 2, and it's running a Bode plot where yellow is the amplitude.
Whoa, wait a second. The software you're looking at looks almost identical to the Joulescope software we were looking at before. It's eerily similar. Makes me wonder if they use the same framework or development suite to build this. But
now this is it measured in degrees here on the bottom. This is phase margin, and all this noise at the beginning, I believe it may be an artifact from being so down low in frequency. This is sweeping from 1 hertz to 10 megahertz.
Mm-hmm.
And I need to go in there and say, well, throw away anything below 30 kilohertz because my coupling transformer just is giving up the ghost. So this is noise, in other words, what I think. But I'm just now coming to terms with what this is showing me. But it's a Bode plot from my Analog Discovery 2. So I'm real happy so far with this new equipment.
Well, in the words of Bill and Ted, that is most
excellent. Bodacious. So I do have to jump right at the top of the hour. So I'm thinking maybe we can start rolling it down here. And any follow-up comments or where were they in stock? Dave Adams asked. Arrow. If you haven't used Arrow is like the old school, except they became the new school. We used to use Arrow as a distributor back in the old days, and it took two months to get stuff, but you could do things like allocation. Now Arrow's website, they sent it to me. I had it in 4 days. So
that's not bad. Arrow was for a long time had the lowest prices but the least amount of stock. And then so for the last project I was wrapping up, which I mentioned those voltage regulators were for that, I ended up specifying parts to be ordered from either Mauser or Newark because they actually had them.
Right.
Yeah, so it's true. Most microchip parts are out of stock. That was at the time I was doing the design work, and by the time they're going to production, it's like, well, I've given you 3 options. So the factory that's going to do the assembly for you,
oh wow,
they can run with what the 3 I said. All 3 of these will work as drop-ins. They may find something else locally. They may be able to get the Taiwan semiconductor part that was overpriced, but because they're buying it for a Chinese factory, they'll probably be able to get it for the price it should be sold at, because they'll be buying thousands of them anyway. So they'll negotiate and work it out, I'm sure.
So basically, you gave them 3 bill of materials and said, figure out which one you can make work.
I gave them 3 options and tested the one that I could actually buy parts for the prototype. So yeah.
Well, that's cool. So yeah, like I said, I have to learn to use variants and the package releaser, or there's the package releaser and project packager and project releaser.
Yes, project packager is just a quick way to archive something once you're done, if you want to just keep it for posterity as a backup. But the releaser, if you're using the releaser, it probably means you're using your 365 workspace, and it also creates a zip file that captures everything at that moment in time.
Right.
It's kind of a backup, and you can then download that. If you don't trust Altium with their 365 hosting, you can just download the whole bundle and save it on your own drive. So
what I've been doing a lot of this last month is not month, but last 4 months is cloning the project to step it. So I leave a variant behind and say, oh, the customer's needs are changing, but I had a good full design. So I'll clone it. And now this is a full working design with new features. So I use that as my point. When DRCs are 0 and everything looks good.
Well, one other way you could do that, and you can do this with any CAD tool. You don't need to be using Altium, but if you're using version control, which you should be, that's a feature that version control gives you, is tagging. So you can say, so if you're using GitHub with KiCad design, you do a commit, and it's a snapshot in time. So that's a really, I used to do it in Altium and other tools. I would do it with SVN. The whole world seems to have abandoned SVN for Git now. So.
Yeah, I have my O'Reilly book on SVN around here somewhere.
I became an SVN guru because it was Altium's internally, and also for integration with Altium Designer. It was their version control of choice for many years, and then Git, the whole world switched to Git for some reason. Git had a few features that made it somewhat better.
Right.
Everyone moved to Git, and now I'm like, I haven't.
Let's just give our code to Microsoft. Yeah, let's let Microsoft hold all of our ideas. They won't do anything nefarious with it.
Yeah.
So somebody wants to know about your shirt.
It's not from Kings in Chicago. Kings X is an old progressive rock band from Texas. They're well known from probably 1988 to current. They've been around for years. They're well known amongst musicians, but not anyone else. Like most progressive rock bands, it's other musicians who know who they are, but not regular people. They've made a living out of this, but never got rich. Let's put it that way. But they're really great.
Right.
Three-piece, fantastic band. I grew up listening to them, so
Very cool. I was listening to old Genesis, Watcher of the Skies, and Supper's Ready before our show today.
progressive rock is the best.
it's so progressive. So, well, hey, I've got to run, but it was great seeing you again, Ben, and it was great showing off some stuff that's going on.
Yeah, and thanks for showing us your new toy. It's always a risk showing people new toys because we all want to go out and spend money
and
get new toys. And I'm trying to get some toys that I actually can justify and use to make money in my job. That
it's all about ROI, right?
It's all about ROI right now. So I'm trying to find ways of getting some sponsorship. Would be awesome, actually, with some of this stuff. So fingers crossed.
Yep. Very good. Crossed. So, all right, we'll see everybody here next week, and you all have a happy weekend and a safe weekend.
Yes, thanks for joining us. Enjoy your weekend.
Excellent.